All right, so we have an optimization problem here to talk about. It says a window is being built and the bottom is a rectangle and the top is a semicircle. Okay. There's 12 meters of framing materials. What dimensions of the window should the dimensions of the window be to let in the most light? Okay, the most light is the area of the window. The 12 meters of framing material is going to be perimeter material. So that kind of makes it a little easier to understand. So the window eye picture would be shaped like this. All right? It's going to have some radius r, and if it's r at the top, we got to agree this is 2r, and it's going to have some height of the rectangle, h. All right, well, I know that the perimeter 12 would be equal to h plus h, 2h, sides, plus the bottom, 2r. And then we know 2 pi r is a full circle, so we have half a circle, so how about plus pi r? That's our constraint. That's the framing material. And what we want to maximize, I'll do it in red, is A, which is 2RH, the rectangle, plus half of pi r squared, the circle at the top. We want to maximize that. Now, we can't take the derivative of that right now because it has 2 variables, r and h. We've got to get to a single variable. So if I save this, and I look at the green equation at the top, I think it's easiest to solve for h and divide by 2. So if I do that, I get h equals 6 minus r minus pi over 2. All right? And with that constraint now, I can plug that in into the red equation for a and get to one variable. I get a equals 2r times 6 minus r minus pi over 2 plus 1/2 pi r squared. And before I take the derivative, because I want to optimize, I want to find a max or min, and this is not related to time, I think it just makes my life a little easier if I do and distribute right away and get here. So I have this equation. And this is an equation I need to optimize. And there's some like terms there. So I might as well combine those like terms. I just noticed that. There's no reason to work real hard here. I'll work down the board. The end two terms are like terms. So I get -1 plus, so how about -1/2 pi r squared? So I want to optimize. So I'm going to do this as a prime. A prime equals, I want to find the critical points. I want to find maxims or mins. This time we want to find a maximum. 12 minus 4r minus pi r. I think that's the first derivative. And I also see then that I can take the second derivative right away. We'll use that later. Let's put it over here. A prime prime equals -4 minus pi. And the thing I catch out of this is that a prime prime is going to be negative when the first derivative of a prime is equal to 0. Thus, by the second derivative rule, we know we're going to have a maximum. So I'll set a prime equal to 0. And I can write 4r plus pi r equals 12. So I can solve for r, 12 over 4 plus pi. So I can use my handy-dandy calculator here, and I can say this is approximately, again, 4 decimal places, 1.6803. And again, since it was in meters, this would be in meters. And again, this is where a prime is 0. So by the second derivative rule, a prime of 1.6803 equals 0, and a prime prime of 1.6803 is less than 0. Thus, by the second derivative rule, we know that this is a maximum. So it asked us to, at the very start of this problem, it asked what dimensions the window should be. Well, we've now found that the radius, r, should be 1.6803 meters. This is a very big window, obviously. So I would tell you the dimensions of the window, and we have an equation to find h. We can plug 1.6803 into there. So I find that the radius is going to be 1.6803 meters, and the height, when you use the equation, comes out to be 3.3 3606 meters. And that would be the window we construct for having 12 meters of framing material. Again, optimization problems really rely on developing these equations at the top in the picture. Keep practicing, keep working.